So, hi everyone. Some of you might remember me. I am Tanner from Supernova. For those that don't know me, I am still Tanner from Supernova. So today we are going to make a spectroscope, but as always, we have a couple preliminaries to go through first. So can everyone hear me and see me? Yeah, you can hear me? Cool. All right, so as you can see, we do have the chat function. And so I will ask you folks to keep appropriate. If I ask questions, please don't just Google them and copy and paste them into the chat, because that's no fun. And yeah, let's just keep the chat appropriate. Besides me, we have another staff member here today. He will be moderating, and he'll introduce himself now.
Hey guys, my name is Yurakami. Like Tanner said, I'll be moderating the chat. Hope you guys have a fun time today.
All right, so we are making a spectroscope today. So I think someone said, what is that? We will get to that. So spectroscopes deal with light and light waves. So first of all, why can you folks see me right now? Any answers? Why can you see me right now? Okay, a different question. A camera? There is a camera, but how do cameras work? We won't get into that. But so why is this green apple different than this red apple? Color? Yep. So certainly the two apples have different genetic makeups because they're different types of apples, but you're very right, they are different colors. And so why do we see different colors? Someone said eyes, and that is certainly right. We use our eyes to see colors, but how do our eyes differentiate between green and red? Well, it's due to wavelengths and the lengths of each different color in a color spectrum. So to start, what are the three primary colors? You folks should know this one. What are the three primary colors? Red, yellow, and blue. Exactly. Okay, quick color quiz. What do red and blue make? When you mix red and blue, they make purple. All right. Yellow and red, what does it make? Mixing yellow and red. Yep, so purple comes from red and blue. You are absolutely right. Everyone that said purple. Yep, orange. So when you mix red and yellow, you get orange. And so one last one, we have yellow and blue. What do you get when you mix yellow and blue? Exactly. So we kind of have a color wheel or a spectrum, as you can see. And so light works the same way, except light's three primary colors are slightly different due to the light spectrum. The three primary colors of light are red and blue and green. So the primary colors with your paint and with color is red, yellow, and blue, but primary colors of light on the light spectrum are red, blue, and green. And so the amount of light that we see is what we see color. So like I said, if I show you this photo, don't have to read it, but it's like a rainbow. This is the light spectrum. And so every different light has, or every different color has a different wavelength. And so our retinas are a part in our eye, our retinas determine the different wavelengths, and therefore we see color. And so that's kind of where the basic sense of why we see color. See, on the screens, every pixel that is collected can be broken down to its base colors, and we can learn even more from that. So astronomers break the red, green, and blue light down as sections, called these wavelengths, and this is broken down into this spectrum. Okay? So, what's the point of, or what is a spectroscope? So, a spectroscope is a device that breaks down these colors and these wavelengths, and it helps us see, especially in space. So, it was a long time ago that a scientist named Sir Isaac Newton discovered that if you shine white light through a glass prism, the light breaks, and it always breaks into the same 7 colors. Say, it's not 7 colors, but it's the 7 colors of the rainbow, and they always break into the same fashion. So it's always red, orange, yellow, green, blue, violet, indigo, or as I learned it, Roy G. Biv. And so red, orange, yellow, green, blue, violet, indigo. Okay, I did indigo, violet. I did it backwards, but it's Roy G. Biv. And so spectroscopy is the study of the function of wavelengths. And so using spectroscopy, we can determine not everything out in space, but that's how scientists use, like the Hubble Telescope and spectrometers. This is how we can understand if there's oxygen on planets, because it's actually, no, I said it right. It's Roy G. Biv. I just said it wrong, but I typed it right. So, yeah, so in space, we can see different chemicals are, when things are hot, they light up, right? You think of fire. When something is very hot, it gets brighter. You heat metal. If you put a fire poker in the metal, it gets really, really hot. So it's actually the same with chemicals. And so chemicals are heated. We can look at the stars, and then we can see what kind of makeup these stars are. So the spectroscope was made a long time ago, or the first invented. It was invented in 1859. And it was invented by a chemist and a physicist. And they were Robert Bunsen. If you've ever heard of the Bunsen burner, he made that as well. And also Gustav Robert Kirchhoff. And Kirchhoff, who is a very famous physicist, because if you were with me in the electromagnet webinar yesterday, he came up with Kirchhoff's voltage law, current law. And so he's very prominent in physics. And so what we can use to see these colors in space is the spectroscope. And so has anyone ever heard of the Hubble Telescope? Anyone? No? Yes? So the Hubble Telescope is a telescope in space, and it was created by a guy with the last name Hubble. And so he is very famous because he was the first one to actually learn that the Earth, or not the Earth, the universe is expanding. So that's why he got the telescope. And so there are different types of electromagnetic radiation, and that is what is our light waves. So we measure waves differently depending on how they are. So like gamma rays, the gamma rays are what we see here. They are measured in nanometers, while radio waves are measured in meters. So I have some pictures I want to show you folks, because what the spectrometer does is determines different colors are broken up into different wavelengths. And so when you look through a spectrometer, you might see something like this. This is oxygen, and that's how that color spectrum, or that's carbon, sorry. Carbon, and that's how that color spectrum is broken down. We have nitrogen, then oxygen, and then iron. And so when you're looking through your spectroscopes, you are seeing different, you would see things like this. Our spectroscopes probably won't be as perfect as these lines are, of course. The metal iron, yes, but iron is an element, right? And so to go a little bit farther, if we look at this picture, it might be a little little far from you, but so on the far right here, or where I'm pointing, that's a nebula. And so the nebula is made up of all kinds of different colors. But if you see on the other side, these are all the same shape, but different colors. Because from my photo, I can see oxygen is green. We have hydrogen is kind of orangish yellow, as well as nitrogen and sulfur. And so we know in this nebula, it's primarily made up of these elements. Yup. The air, oxygen, yup. And so air is actually not just completely oxygen, by the way. Also, it's like 79% nitrogen, 21% oxygen, I do believe. Just a fun fact for you. So why don't we start our little spectroscopes? Let's go over our materials, shall we? So do we all have a roll like this from paper towel or toilet paper? Toilet paper would be a little tiny. Paper towel would be more ideal. Do we have this? I will assume we do. So I have my paper towel roll. I have a CD. See, the CD already shines in the light. That's because there's already ridges and scratches on this CD right here. And so you often get the rainbow colors and the interesting patterns because these are called interference patterns. And so that's why the CD is going to work for us, because we're going to kind of run the same interference patterns. So I have my CD. I have some tape. Any tape will do. I'm using black tape because we're working with light. So when you want to see specific elements of light, it's best to kind of have the surround be dark. So that's why I'm using black tape. I didn't say so. It won't affect your spectrometer all too much. I also have some scissors and a pen. So I told you folks that when the materials list came out that paint was optional. I'm not going to paint today, but that is for if you want to make your spectrometer a little bit prettier, then by all means paint this. But that would be a first step because you don't want to paint it afterwards because that'll just be a little messy. So if you want to make another one, or this video is being recorded so you can rewatch and make another one if you want, and you can paint it. So the first thing I'm going to do is mark up where I'm going to cut parts of this paper towel roll, because the cutting is a pretty important part to this. So the idea is we are going to cut a line into this paper towel roll, but it's going to be at a 45-degree angle. So for some of you that if you don't know what 45 degrees is, so this is 90 degrees because that's 90 degrees. 45 is half of that. So I want you to cut it at an angle of that. So into the paper towel roll, kind of like that, if you see what I mean. So I will start and just cut it. Be careful. You will have to fold it a little bit. That's totally okay. That happens. I fold it too. So I'm trying to fold it at 45, or I'm cutting it and folding it at 45 degrees. And I'm only cutting into half. I'm not cutting it off because this is what's going to hold our CD. You see? So the CD is going to go in here at a 45-degree angle. So the next step is, oh, I actually need that. So the next step is going to right across. Did we all cut our 45 degrees? No? Okay, I'll give you a couple more minutes. So I have some other examples. I have some right here that kind of looks better. So just look at that, the way it is. Perfect. And then it fits in like that. I'm not telling you to put your CD in yet. I'm just showing you that that's how it goes. It is a little tricky to do with the scissors, but box cutters work better, but don't use a box cutter unless you have absolutely permission from your parents because they are very sharp. So we have this. I have my CD in, and I have my cut. So the next step is we will, so don't worry about it if you're not caught up. This is a quick little craft. The craft is, or not craft, experiment here. So manufacturing the prototype doesn't take a lot of time. So even if you are far behind, it won't be difficult to catch up. So if you see here, what I have is I have my line right here where I will put my CD, but then on the exact opposite side, I have cut a little hole. So what is that for? Well, when I put my CD in, you want to be able to see the CD. And if you look up in the sky, you'll start seeing more of the spectrum. It will be broken up more into this. And so that's kind of the idea that for a spectrometer, the spectroscope, when light is broken down and scattered in a way larger scale, you start to see the black bars that separate light from each other. Because if you look at this, this is blue and purple, but they're right next to each other on the rainbow. So in a sense, you understand that there's just space in between, and there's different spaces in between depending on the chemical we have. So I will my hole now. I have my 45 degree, and then on the exact opposite side, I am going to cut a square. So it's a little seeing square. I would recommend maybe one this size. It's something for you to just put your eye through. So it doesn't have to be huge. It's just something you want to see. And remember, it has to be directly across from where you have your 45 degree CD, because you want to just see the CD at 45 degrees. So the light you're seeing is bending and going up. Does everyone know what I mean? Yep, okay. So I am cutting my hole, just a little one. This is it's not the easiest cutting when you have to cut into something like this, so I know it might take you a couple times. As you can see, I have had much practice. So now I have my hole, and I have the slit. And now we're going to put that down. We don't need to put the CD in yet. Actually, we want to keep this in our hand because our next move is making the lid to this. So we don't want just an open hole that we can see through. What we want is something that looks like this. And so all it is a circle that covers the top, but it also has another tiny hole. So make it about the same size as the hole right here. So what's the best way to make your circle? Well, I have this, and if you have a pencil or a marker or whatever, put your bottom here and trace a circle, right? So if I take the size that I want, and then I trace a circle, I know I will have a circle that is the perfect size to cover my spectroscope. So it's okay if your circle on your spectroscope is slightly larger. It isn't good if it is slightly smaller. You want it bigger rather than smaller for sure, because we are trying to eliminate any light coming in from any other except for the spots that we have designed. So right here and right here. And that's kind of manipulating the way light comes to investigate it a little bit more. So I am cutting my circle, I have a circle here, and there is one last part to cutting. That is putting in the little slit here that we're gonna see, and this is gonna be pointed to the sky. I know it's cloudy today, so you might not be able to. This is a lot better outside when you're looking not directly at the sun. Do not point this when you're looking directly at the sun. We know that. But anywhere else outside, when you're using that, you'll see a lot better color than the light here. So I am cutting this. To make the slit, and then all I have to do is have my hole here. I have this here, my cut, and so you want it on this end. How is everybody doing? Are we staying with me? How's it going? We're pretty quiet today. I'm hoping we're staying along. So, good? Okay, thanks for answering. I very much appreciate it. So, like I said, I am using some black tape. I have two types of black tape here. I have some electrical tape, and I also have hockey tape. So, but all tape works. But like I said, the black tape is just a little bit handier because it does remove all the other light a little bit better than, say, clear tape. So I have that like this, and I'm just going to put 4 pieces on the top, 1 piece on each side. Does anyone remember the name of the space telescope I mentioned? It rhymes with bubble. Herbal? Close. Hubble. So that could just be about that's probably just autocorrect. I'm sure you knew what I was talking about. It is the Hubble Telescope. And he is famous because he discovered that the universe is constantly expanding. Wouldn't that be something to learn? So I have my 4 pieces of tape here. Voila! It would definitely look a lot nicer if I painted it, but I'll give you folks that option to do on your own time. So I have my lid here. When you put your CD in, I have 2 sides of the CD. This CD has wording on this side, so this is the top. So I want the bottom part. So if you're putting it in a DVD player, you'd put it in like this, or if you had a video game, it'd be this way. So it's the bottom. It's the bottom of the disc that you are going to be looking at. And so, like I said, this won't work great inside. It'll work better outside. So I encourage you folks to go try that after the webinar. If you see here with the cut, I have little parts here that light can shine through. I recommend trying to cover those up. I will do that now. I'm going to put a little black tape where I can fit it. Just because we are trying to, like I said, eliminate any light coming in from any other spot. Besides where we want to look through and where the light bounces off and goes through there. So take a couple more pieces of tape to eliminate some of that light coming in. The Hubble Telescope is incredibly famous because it has done a lot. It has recorded black hole signatures. It's recorded black hole signatures. It's uncovered gas swirls. There has been a lot. provided, or it first detected the atmosphere of a planet orbiting the star outside of our solar system. So I know that doesn't seem like a lot, but that's very, very far away to detect something like that. So might not work perfectly. A box cutter definitely would be a better incision, because you almost don't want your cut to be a triangle. It would almost kind of be better to be a semicircle, but that's incredibly difficult to do when you're cutting this. So with just straight up scissors. So I have a little light lost. Perfect. And I'll leave it like that for now. So what we want is, what you're going to probably do when you're looking through it is you want this bottom part also covered. So you can cover it with your hand, or if you use, like, put it on the ground, on a deck somewhere, and then you can just simply look through the hole, and you will definitely see a rainbow, because you can already see a rainbow. And look, the rainbow should be a little bit more distinct. Now, like I said, it doesn't look great inside, but definitely go check this out outside after the webinar. So, do we all have this? Do we have our spectroscopes? I will assume we do. Okay, folks. Well, the only other thing I want to talk to you about, and yes, perfect. If we're finishing our spectroscopes, it'll be good to know. I want to show you another cool thing about light, and that is the idea of refraction. Now, we're not going to get too busy into this, but I just thought it would be really cool to see that. So light moves, there's light waves, there's colors, but light also can bend and turn, and that is called refraction. And that is because, so it's deflecting, right? So light deflects off this and goes up. You've heard of light reflecting, because when light reflects, we'll say you're looking at a mirror, that's light reflecting. But refraction is when, so if I have this glass of water and arrows, so we see these two arrows, they're going the same way. Well, when you put the arrow behind the water, it's going the other way, isn't it? Do we see that? So how does that work? Well, light, when it bends through mediums like air or water, especially water, it bends. So the speed and direction of the light slightly changes, because we all are familiar that light does indeed have speed. And so that speed can change depending on what it goes through. And so the direction changes, kind of like when a direction changes here, the direction is bent all the way. And so it travels through the air, the water, back to the air, which causes it to go the opposite way. All right, folks. Well, that is what I have for you today for the spectroscope, our spectroscopy. I hope we had fun. I do have a couple quick questions for you. It's not a quiz, but if anybody wants to answer that. So, what was the name of the famous telescope? We know this. Yep, the Hubble. Hubble. Can we name either two of the people that invented the spectroscope? One of them was a chemist, one of them was a physicist. One of them has a lot on voltage and current. The other one has the Bunsen burner. So it's Robert Bunsen and Gustav Kirchhoff. So a couple really, really smart guys for sure. So those were two questions. I just wanted, let's refresh it. So in case we had forgotten, that is all I have for us for today. We have made a spectroscope. I know some of us are still working on it. So if you are still working on it, I'm going to be here for the next 5-10 minutes, as I always am. And I would love to answer any questions you have about the spectroscope. For any of you that are done, you are welcome to go. the way you leave is top left corner. You can click that and click leave session. Or you can click your little fella and then your little name tag at the bottom and click leave session. Thank you for coming, and bye everyone.